Hi everyone, video 2 on Comep and Wep, so energy transfer. Right, really like this example because it kind of puts everything together. So let's just go for it. A skier passes a point A on a ski run. So let's say this is A, yeah? Moving downhill at 7 meters per second. So 7 meters per second, that's what they start with. Okay. After descending 100 meters vertically, the run begins to ascend. And when the skier has ascended 30 meters to the point B, her speed is 4 meters per second. So U is our initial, 7 meters per second. It then ascends, then descends for 100 meters. It's not going to be a vertical 100 meters, is it? A slope, otherwise she'd die. So it's going to be a slope like that. And then, well, a gentle slope. Depends what color the ski run is, doesn't it? And when the skier, it begins to ascend, and when the ski goes to 30 meters, so again, that's not going to be vertical. Good luck jumping up that. And that ends up here at point B with final speed 3 meters per second. 4 meters per second. Okay, now it says the skier and her skis have a combined mass of 60. Okay, so 60g, that's cool. The total distance she travels from A to B is 3,000 meters. Now let's be very clear what that means. That means she runs along the surface of the snow for 3,000 meters. It does not mean the straight line A to B is 3,000. It means the slope A to B is 3,000. The non-gravitational resistance to motion are constant, important word there, and have total magnitude 15 newtons. So that's basically saying the friction of the skis against the snow is consistently 15 newtons all the time. Every meter that person travels, they have to overcome 15 newtons of resistance, right, in order to move. So let's calculate the work done by the skier. Now that immediately insinuates that the skier is putting effort into making this happen. They are moving their legs, pumping the thighs in order to get that motion, get that speed up. Okay, so they are applying work. So if we're applying work and there's resistance here, immediately I know this is Wep. This is not Comep because there is external forces here. So I quote my formula. So final EK, initial EK, plus or minus work done against gravity, plus or minus work done against external forces. Boom. Okay, let's go for it. So final EK, what's that? So that's half mass. Mass is 60, and the velocity is 4, so that's squared. Initial EK, half mass, 60. U is 7 squared. Plus or minus work done against gravity. Okay, let's think about this. Now I want to clarify, because I think in the other video I kind of used work done as saying force times F. I don't want to use D because we use that for moment. So Fs, and I think I interchangeably use displacement and distance. I just want to clarify, S is distance moved by the force. Distance moved by the force, right? And the reason I said displacement originally was because of this work done against gravity, okay? Because work done against gravity, I don't care if this woman has flown to the moon and back, right? And then comes back down to this point here. It doesn't matter what happened up here. All we care about is where she started and where she finished. So what is this gap here? Well, it's 70 meters, isn't it? Okay. And have they gone down or up? Well, they've gone down. Gravity works down, so that must be positive. So mgh, yeah, 60g, and the h is 70. Now you might be thinking, well, if s is distance traveled and work done against gravity is mgs, where mg is the force and h is the distance, you're right, but think about it. Whatever comes up and comes back down, that mgh is cancelling out, isn't it? Because it's mgh up and then the same mgh down. So it's neutral. It's net zero. Okay, so it's displacement in a way. That's why I use the word displacement. But it is really distance traveled, isn't it? Because I can push, like if you're talking about, well, if we're talking about this external force 15 newtons, right, which we can deal with now, so plus or minus work done against external forces, for the entire 3,000 meter surface of this slope, they've had to deal with this 15 newtons, right? But you could argue the displacement is kind of this diagonal line, but that's not really what we're talking about, is it? Because this 15 newtons force, remember, work done is, sorry, it's not in this direction, is it? Work done is defined as the direction, the distance someone has traveled with the force acting on it. So that plus or minus WE, is it plus or minus? Well, it has to be minus because the person is moving down the slope, along the slope, but that 50 newtons is opposing her the whole way. So force times distance. Force is 15 and the distance is 3,000. Okay, so what I'm trying to say is that for work done against gravity, it is like mg times displacement, isn't it? Because any movement up and down is just going to cancel each other out. So in the end, it's the displacement that counts. Other forces, however, you can clearly see what's happening. That force is continuously acting on that person for the whole duration of that ski journey. And it is distance. It is distance. Okay? Right. So we've done that. That's our plus or minus work done against external forces. But is that all of the external forces? No, because the skier is also putting in work and energy and a force. And is the skier going to be opposing themselves? No, they're going to be trying to help each other out, well, help themselves out. So this has to be work done by skier. It's not asking what the force is that they're applying, okay? Don't need to know that. It's just asking for the work done. So what I'm saying is that this work done against external forces, that includes the 15 newtons and the work done by the skier. The biggest mistake people make is just putting in the force and not the distance. So that's why I always put W equals Fs at the start of all my work. So I know, yes, I need to include that. So work done by skier, if we work that out, so we've got 0.5 times 60 times 16, subtract 0.5 times 60 times 7 squared, subtract 60 times 9.8 times 70, plus 15 times 3,000. So I get 2850 joules. Remember, if I didn't put that WS in there, I wouldn't actually be finding anything. Okay, cool. Next example. This is great because this links to projectiles. Love this because it makes projectile questions so easy to find the height of something, or anything to do with velocity and links between the height. So I've got a particle projected from a point 50 meters above, so 50 meters, with angle alpha. But what we see is, don't really care what alpha is, okay? And it's the whole speed is 10 meters per second. Okay, so this is u, isn't it? U is 10 meters per second. Hits the floor with some v meters per second. It says find the speed at which the particle hits the ground. So it's not asking for vertical or horizontal, and I don't need it. That's what's so good about Wep and Comep. Now, is this Wep or Comep? This is Comep, isn't it? Because there's no external force. It's just gravity and kinetic energy. There's no air resistance or anything like that. So Comep, we know, is final EK equals initial EK. plus or minus work done against gravity. So final EK, half mass, v squared. V is the thing we're looking for. So half mass, v u squared this time. So that's 10 squared. Notice I'm not writing 100, or I'm not writing a half times 100 is 50, and I'm not writing 50 straight away. I'm showing the examiner every part that's going into that formula first before I start simplifying things up. Is it plus or minus work against gravity? Correct. It's minus. Because even though this thing started going up, again, I don't care if you've gone to the moon and back. It's where you end up that I care about. So it's plus, isn't it? Because gravity works down. And in the end, the thing has traveled down. So mgh, which is 50. So therefore, I can find v because the m's cancel. And some of you smart asses will say, oh, can I just cancel the, can I just not write the m? No, you have to write the m. The examiner requires you to put the full formula down, okay? And divide by 0.5, square root that. So 6 root 30, so 32.9 meters per second to free SF. Remember, you're working with G, so maximum free SF. B says calculate the loss in potential energy. Loss in potential energy, that just means calculate the work done by gravity, doesn't it? Because gravity has worked, the thing has moved down, it had a load of potential energy here, but then it's all dissipated and it ended up down here and it's gone. It transferred to kinetic energy, okay? So calculate the loss in potential energy, that's literally just asking for work against gravity. So that's mg times by 50. We don't know what m is, so we're just going to leave it in terms of that. So 50 mg. Okay? Joules, remember, because it's work. Okay, that's the end of that video.